weight. Because my weight is between me and the earth.
Yeah.
I am not affecting my weight on the scale.
It's measuring the normal force of you on the scale.
Yes. If you've ever stood on an analog scale, when you step on it, does it immediately like that go to your weight?
No.
Or does it go shooting past and then eventually reach there?
And those digital scales have to zero out, so that's why they have you step on them first.
Oh, okay.
Yeah.
If this actually measured my weight, then I can have instant weight gain and weight loss. Look at that. I'm about 400 pounds. Oh, no, about 50 pounds. It's not measuring my weight. It measures the normal force. Because that is the force I exert on the scale. Now, why do we say it measures weight? Well, if my acceleration is 0, in whatever unit you want, then the total force on me, total force on person, is also 0. There's a direct connection between force and acceleration. I alluded to it earlier. We will get to it officially when we're done with this, but the relationship between force and acceleration is force to the mass times the acceleration. This is total force. So if I'm in equilibrium as I stand on the scale, then my upward force, the force going up on me, equals the downward force. Then the normal force that the scale exerts on me, which is equal in magnitude to the force that normal force I exert on the scale, would be equal to my weight.
So you're saying, like, if you're not like jumping up and down, the two forces equal each other? Okay.
Yes. And the reason why I did not just enthusiastically come out with yes,
Yeah.
is because that works fine until we get the rotational motion, and then suddenly you realize, well, I'm not actually in equilibrium because the earth is spinning.
Okay.
But the difference between my weight and what the scale is reading with it, taking the earth spinning into account, my weight's about 1,000 newtons. I think it was somewhere around 2 newtons difference.
So you're just saying that stationary objects, well, a stationary object on top of another one.
Objects in equilibrium.
In equilibrium, okay. Or the normal force is equal to the gravitational force.
Yeah, in this simple thing. All right. Questions to hear?
So, hold on, so if your scale is measuring the normal force of you on it, but there's also a gravitational force pulling you down, wouldn't that be that our weight is relative to the Earth? So on Earth we're 200 and whatever pounds, and then on Jupiter or the moon we'd be like 90 pounds.
Yeah, on the moon it would be roughly 1/6 of what it is here on our moon. So my weight would change, and therefore the normal force would change.
So so weight only, okay, so weight differs on whatever planet, place you're at with gravitational.
Yeah,
Think of box falling.
Yeah,
This box falling, the only force acting on the box was its weight.
right.
In a direct application of this formula right here. The force was the weight. The mass is the mass. And for a box in free fall, it's the acceleration due to gravity. That's the formula for weight.
Okay.
That is something that you should know. We'll be using it enough. You know, right now, if I said, what's the formula for weight, and you go, that's fine. A month from now, if I say, what's the formula for weight, and you go, that's a concern. And there's also another, this is a well-used formula in physics. Pretty much any physics textbook is gonna have this in there, so any beginning physics textbook is gonna have this in there. if you have one of those automatic readers that read text, I've yet to find one that actually will read this as W equals mg. It reads this as W equals milligrams. Yeah.
I'm not 200 pounds today, I'm 200 milligrams.
That's right. And so, since little g depends upon where you are, depends upon the planet or where you are on the planet, that's where the weight gets affected mathematically. All right, questions on this, because we're about to do box on ramp. Ooh, yeah.
Don't miss hanging.
Heating up.
That woke me up.
So we're at 6, so 7 will be the next one. Notice that I made the ramp part of the ground. I don't want to deal quite yet with what if the ramp is detached. We'll do that next. All right, so the first thing I do is I draw my drawings. Now I recommend that you draw the box in roughly the same orientation that it is in the original problem. Some people like to straighten out the box, and that there are a couple of exceptions, but usually students who straighten out the box really mess up the direction of the forces. Is there anything we can eliminate?
Tension
Okay,
and other.
so obviously we've now introduced another force. Let's start with weight. Which way is the gravitational force acting on the box?
Directly down.
Matter of fact, the direction of the gravitational force is what defines the word down. And then the other part of that pair?
Goes up.
So that's from the earth going up.
All right, now, one of the questions that I sometimes get is, does it matter where I actually draw the up arrow? It should be touching the ground. The ramp is part of the ground, so yes, the box is here on the ramp, and so it's fine to put the weight here, but you could draw it here, or here, or here, just somewhere on this thing that we're calling the ground. Then draw it only once.
So we can't draw it on the ramp, is what you're saying?
You can draw it on the ramp, that's fine, because the ramp is part of the ground.
Right, okay,
If the ramp were separate, then don't.
okay. Well, it'd be a separate part of the
Yeah,
thing.
we'd have a
Probably-
third object.
Yeah, we'd have to, yeah.
All right, so weight is done. I have only, besides my planet here, I've got only one object, so I'm gonna have only one pair of gravitational forces done. Let's do normal force next. I'd like someone to be bold enough to talk about the direction of the normal force on the box.
It'll be,
Is it gonna be like diagonal?
yeah, it'll
Perpendicular.
be going up from the box.
You know, I appreciate the fact that the first people who spoke did not say the wrong thing.
Aw,
What is the thing that most people say wrong?
it's like
Up.
still up and
Yeah.
down.
There's, because all the beginning problems have, this is my theory, all the beginning problems have the normal force opposite the weight. People seem to get that stuck in their head of that's always the way it is. It is not. Normal force is indeed perpendicular, which is why I went through that bit of what does normal mean. It is this way and that way. It is still perpendicular to the ramp. Now, as the angle of the ramp gets smaller and smaller, that normal force will get closer and closer to straight up. There we go. Got it. But if that ramp were at a 90-degree angle, yeah, that normal force is perpendicular to the weight. It's still acting down. And now friction. Questions on normal force before we tackle friction? All right, friction. What is the desired direction of motion of the box?
Down to the right,
And therefore the friction is acting.
up and to the left.
I love the units for friction. Or the
Me too.
symbol.
Simple.
It's very easy. No dash on the W.
It's a little bit of flair that gives physics style. You know, when our wardrobes don't scream style, I gotta put it somewhere.
Makes me look really smart when people look at my homework.
Does it matter which arrow we put like closer to the ramp and closer to the box? Cause like, wouldn't it be flipped actually? Wait, no. it wouldn't.
Friction opposes the desired motion, so
Right.
this desires to move down the ramp, so friction's gonna oppose
Okay.
that. Yeah, it does matter which way the friction arrow is pointing.
Okay.
Now, there are some, the complex force diagram problem, there are times in which I have a very clear image in my head of what's going on, but later on I can read the text and go, oh, wait a second, I guess that friction could have gone either way, depending upon other things. So, in those cases, again, that's one of those things where I grade it and I'm marking people wrong. About halfway through it, I realize, oh, there are multiple interpretations for this. So I go back and I look at it, these people who have done it already, and correct those. Anyway, force diagram. A couple things here. What is gonna be, since it's gonna accelerate down the ramp, what is gonna be the acceleration, what is the direction of the total force acting on the box?
Down into the ramp.
Yep. So if I add these, so if that's the, whatever the angle that is, if I add these three vectors together, so it doesn't matter which one I start with, I'm gonna start with normal, weight, friction. Play net force
It's still going down.
down the ramp. Or friction is strong enough, then, you know, potentially it's not moving at all. There are things on angles that don't move. So they tell me.
I'm sorry, I might be confused. When we went up, I'm sorry, it's the right, down. So.
Because normal force is up and to the right,
Right,
weight is acting straight down, and friction's acting up the ramp.
when we add them together, I'm trying to think of what would cancel out so that we would get straight down, or not straight down, but slanted down.
I'm not sure I'm following.
I'm confused where we got down and to the right. And I know it's because we added those together, I just forgot how to add them together, I guess.
I know it's gonna go down and to the right because physically, if I put a box on the
Yeah.
ramp, that's the only way it's gonna accelerate.
Right,
So I draw this that's supposed to be perpendicular to my dotted line here.
right,
I drew this straight down to basically the dotted line because I know that's where I have to end up.
okay,
If I just, without any context, just gave you the arrows and said add them, then the arrows would have to be drawn the correct length, going back to the question Anna had asked earlier.
mm-hmm,
But because there's a context here and I know my net force has to be down in that direction, I just drew weight how I got there.
so it's a rough sketch, it's not like legit, we just know from the problem, we're not like legitimately adding up those vectors.
Yes, we'll actually do proper addition
Okay,
with trig.
okay.
Lisa?
Wait, so that first drawing is the force diagram,
Yes.
but what is that second drawing called?
This is the sum of the forces.
So,
Because the total force is equal to mass times acceleration. And so like, I was adding them up to just show that's my total force right there.
okay, but why wouldn't, like, I get how there's gonna be two frictions, like, going like that, but wouldn't there be another, like, shouldn't there be another arrow for weight going up?
No, we're only adding the forces acting on the box here.
So then why?
The up arrow is acting down here on the ground.
So then why did you draw a triangle then? Oh, those are arrows, okay.
Yeah, these are these three arrows here, and then that's my resultant.
Alright.
So I have a question then.
Yes.
If you were, since all of the forces acting on the ground are equal in magnitude,
Right.
those acting on the box, then if you were to do the same thing with the arrows that are acting on the ground, wouldn't that sort of imply that the ground is moving? Because it, I mean, it seems like it should be net zero because the ground is not moving, but the resultant should be the same, just in the opposite direction. So, sorry, that was very convoluted, but like,
So if we did the sum of the forces on the ground, we would have a, we'd have a resultant arrow pointing up.
right, but the ground itself is not moving.
We pretend it's not.
It just seemed like the conclusion we came to is that the resultant is pointing down into the right to the box because
Yeah.
the box is moving, and if you get a resultant arrow to the ground pointing up and to the left, just,
Yeah, there's a net force acting on the earth, but it's small enough that it doesn't really move the earth any, like, noticeable amount.
right,
Because anytime I do this experiment, there's someone on the opposite side of the world also doing it.
right,
It
right,
bounces
right.
out.
They're jumping while we're jumping.
Yeah.
Yeah. Exactly.
Nice.
Yeah, then there is a certain sanity to it ultimately ignoring what's happening to the earth. That was from a physics point of view, I'm not talking about
Yeah.
global warming, anything like that. Notice, there's some angle here. Some angle there. Since this is a right triangle, despite the way I've drawn it. So right now, let's assume no friction. We'll make it frictionless, and so basically I have normal force going this way, and I have weight going down. There's weight, there's normal force. The normal force is not pushing this thing down the ramp. It's perpendicular to the movement. The weight, on the other hand, part of the weight is causing this box to move down the ramp. So what I want to figure out is how much of the weight is down the ramp and how much of the weight is opposing normal force. So in essence, I'm breaking my weight up into perpendicular components. Now, that's a right angle over here. This angle or this angle, one of them is equal to theta. The question is, which one? Well, I know this angle down here is theta. Therefore, this angle right here has to be the complement of theta, which I'll mark as theta prime, which means that this angle up here must be theta. Which tells me that for my force diagram here, weight times the sine of theta is down the ramp, because it's opposite my theta here. So I have weight times the sine of theta down the ramp. I have weight times the cosine of theta into the ramp. I have normal force pushing away, and then potentially there's friction acting back this way. In the lab, and I jumped ahead some steps because I know the lab's coming up again. We're just going to get the measurements down on Wednesday. It won't be due for 2 weeks after that because the test is a week from today. Oh, sorry, strike that, a week from Wednesday. But I at least want you to have some familiarity, so when you look at it later, you go, wait a second, he did mention something about that. Since this object is not accelerating off the ramp or into the ramp, it's not suddenly levitating and it's not suddenly digging into the ramp, those have to balance. At some point, there's a question of what's the theoretical normal force? Well, it's the weight times the cosine of theta. And weight, you had that formula already, W equals mg. If it's frictionless, then W sine theta is the net force acting on it, and that's going to be equal to mass times acceleration. This, if it's frictionless, this is the theoretical net force. Can't remember the wording I used in the lab, but that's. So you're going to experimentally measure what force is required to keep it from going down the ramp, and there'll be a place to compare to what theoretically it is if indeed it's frictionless. And then there's a question in there about is that a legitimate assumption that it's frictionless? And again, some of the stuff we just haven't gotten to yet, but the vocabulary at least could ring a bell of some sort. Justin?
Are we taking it that that top angle in that diagram there is theta because it's opposite of that, theta prime there? Because-
Yeah, in a sense, yeah.
Okay, I just wanna make sure I was using that
Yeah.
for the right.
If that's a right triangle and that's 90
Right.
degrees, then those have to add up to 90.
Okay.
Well, isn't there also some kind of like adjacent, angle deal, where if you have an angle on an edge right here, and then there's another angle up top, it would be the same as those?
Oh,
Yeah, if you drew a line there,
Yep,
then,
those two should. The one that you
or
drew in
this
green.
one.
No, the one you drew, what I'm saying is, when you've got, an angle, that's the one that you drew in black, the angle, not prime, yeah, that one should be the same as the green one, because that's a adjacent angle, something like that.
Oh,
yeah, I was gonna say, that doesn't make sense, because if you do like opposite angles, the one in the top left corner, that should be theta, which means this, no, wait,
well, that one should be theta.
yeah, that one's gonna be theta, then the corner where the red and the black, that should be your theta prime, right?
Yep.
Yeah,
So that is theta, okay,
Oh,
that makes
okay.
sense.
That
There are
makes
several ways of getting there.
it'll mirror all the corners.
We've made
too,
it a
right?
very complicated way, but I
All
see.
the same.
Yeah. Ultimately, what we're eventually gonna get to is if you're given the angle off the horizontal here, down the range study of sine theta. We're gonna I'll go through this again when we actually get to where I usually introduce this, but shortly after that, we're just gonna go, down the ramp W sine theta.
Okay.
Which still doesn't prevent some students from flipping sine and cosine, but hopefully it'll be fewer.
I just wanted to make sure I wasn't making a wrong assumption about why we had this thing.
Oh.
That confirmed the votes.
Okay. I want to detach the ramp from the ground. They're supposed to be touching there. That's supposed to be a box. Basically detach the ramp, that was a better drawing over there. Force diagram. A lot of it's very similar. We still have weight